Types of chemical reactions. In this lesson, we're covering the 5 types of chemical reactions, specifically synthesis reactions, decomposition reactions, single and double displacement reactions, and then combustion reactions. Learning objectives. In this lesson, we're describing the 5 general types of reactions, as well as being able to predict the products of these reactions. Types of chemical reactions. The 5 types of chemical reactions that will be covered include synthesis, decomposition, single and double replacement, as well as combustion. Part 1. Synthesis and decomposition reactions. Synthesis reactions. A synthesis reaction occurs when 2 or more substances combine to form one substance. The general form is A plus X gives us AX. So we have more than one thing becoming one thing. So an example of this is magnesium plus oxygen gives us magnesium oxide. So you can see we have magnesium plus oxygen, 2 things, giving us magnesium oxide, 1 thing. Synthesis reactions. Synthesis reactions may also be called composition or combination reactions. You got to keep that in mind. Another example of a synthesis reaction is potassium plus chlorine gas. And what that's going to make is potassium chloride. So we have 2 things, potassium and chlorine gas, going to give us 1 thing, potassium chloride. And that's what we have here. Now to balance this reaction, we're going to balance first of all the chlorines, because we have 2 chlorines on the left, so we're going to balance by putting a 2 in front of the potassium chloride. Now we have 2 potassium, so we're going to put a 2 in front of the potassium. And now we have a balanced chemical equation, as shown down here. Here are a few other synthesis reaction examples. These don't need to be memorized. The point of this slide is to show you what it can look like. So it doesn't need to be 2 single elements making a compound. In this case, we're going to have a compound plus another compound giving us a 3rd compound. But again, we have 1 thing plus another thing giving us 1 thing. Second example, barium oxide plus water gives us barium hydroxide. Now you don't need to predict this. That's another thing. In this part of the lesson, it's just about recognizing that this is a synthesis reaction. You don't need to understand that barium oxide plus water gives us barium hydroxide. You just need to identify that that is a synthesis reaction because you have more than 1 thing giving us 1 thing. Same thing with the 3rd one. Sodium oxide plus carbon dioxide is going to give us sodium carbonate. Again, more than 1 thing giving us 1 thing. Synthesis reactions. Elements or compounds combine to form one product. That is the key thing, the one product. The only synthesis reactions you will be asked to determine will be the very simple ones with only 1 possible answer. So for instance, A plus B gives us AB. Or in our previous example, potassium plus chlorine gas gives us potassium chloride. Decomposition reactions are kind of the opposite of synthesis reactions. So synthesis reactions, where more than 1 thing becoming 1 thing, decomposition reactions are going to be 1 thing becoming more than 1 thing. So the general formula for that is AX is going to give us A plus X. So for example, water can be decomposed by electrolysis. So you have water breaking down into hydrogen gas and oxygen gas. So you have 1 thing becoming more than 1 thing. And again, here are some examples. You don't need to be able to predict these examples. You just need to be able to understand that it's 1 thing giving us more than 1 thing. 1 thing giving us more than 1 thing. And so on through all the examples. Decomposition reactions. Some substances can easily decompose. So for instance, ammonium hydroxide is actually ammonia gas dissolved in water. Some acids also decompose into water and an oxide. So for instance, sulfuric acid is going to make water and sulfur dioxide. But like synthesis reactions, the only decomposition reactions you'll be asked to determine will be the very simple ones with 1 possible answer. So water decomposes into hydrogen gas and oxygen gas. We know that hydrogen and oxygen both must be H2 and O2 respectively because they're diatomics. So that's going to make it very easy to predict the products of that. And water can really only decompose into its constituent parts, the H and the O. And that concludes part 1 of types of chemical reactions. Single displacement reactions. In a single displacement reaction, a metal will replace a metal in a compound. So the general formula is going to be A, so that's going to be our metal, plus BX. Now the B is going to be the metal because it's written on the left-hand side. The X is going to be the non-metal. Gives us AX plus B. So again, that's the metal. They replace the metal. So this must be the non-metal there. So this A is essentially going to kick out the metal B, and that's why the B is by itself. The X is left, and the A is able to bond with it because we're going to have a positive A ion and a negative X ion. A non-metal will replace a non-metal in a compound. So same thing. So I talked about the metal bumping out the metal. Well, you can also have a non-metal, so in this case the Y is the non-metal, bumping out a non-metal. So it's the non-metal here, it's going to be the X because it's on the right-hand side. The B here is going to be the metal. So this Y is going to come along, and it's going to knock that X out, and that's why the X is by itself. That leaves the positive B and the negative Y to form the compound BY. And since we always write the positive one first and then the negative one, our compound is BY and not YB. So here's an example of a single displacement reaction. We have nickel plus silver nitrate. So what's going to happen here? Well, the nickel is going to replace the metallic ion Ag. That's because nickel is a metal and the Ag, silver, is also a metal. This NO3 is going to be our polyatomic nonmetal. So the nickel is going to come along and bump out the silver. The silver becomes free silver and the nickel becomes the nickel 2 ion. So now to figure out that it's nickel 2 and not nickel 3 or nickel 1, you need to be given a little bit more information. So that's where this part comes in. So you need to be told a little bit more information in order to figure out what the resulting compound is. But since we know it becomes the nickel 2 ion, what we're going to have is we're going to rewrite our formula here. So nickel plus silver nitrate. The nickel is going to come along and bump out the silver. So we know we're going to have silver by itself. And it becomes free silver. Free silver is a solid. That's going to be an aqueous. And that's going to be a solid as well. So what we're going to get is we're going to get the nickel bonding with the nitrate. And we're told it's nickel 2, so it's Ni bracket NO3 2 plus our silver. And that's what we have here. So now we need to balance the equation. So let's pick an element to go with first, or a compound in this case. Let's balance our NO3s. So I'm going to rewrite the equation. Ni plus Ag NO3 gives us Ag plus NiNO3 2. Let's balance our nitrates. We have 2 nitrates on the right, so let's put a 2 in front of the Ag on the left. Now we have 2 Ags on the left. Let's put a 2 in front of here to make it 2 Ags on the right. The only thing left is nickel. There's 1 nickel on the right. There's 1 nickel on the left, so we're good. Thermite reaction. So as you saw in the video, that was called a thermite reaction, and it produced a lot of energy. So what exactly happened? Well, in this case, the aluminum replaces the iron 3, and the iron 3 is left out on its own. So we know our reaction is going to end up with an Fe over here. Now, how does that happen? Well, the positive Al is going to replace the positive Fe. So it's going to bump it out. So we know our reaction is going to look something like this. Al bonding with the O plus Fe. Now, how do we figure out what our products will be? Well, let's just do it down here in the bottom right-hand corner. So we know when we're making a compound of aluminum and oxygen, just like when we're writing any ionic compound, we need to put our charges out. So aluminum we know is +3, and oxygen we know is -2. When we do the crisscross, you're going to get Al2O3. So let's write that up here. Al2O3 plus our Fe. Now Fe just becomes iron, so there's no charge on Fe. There's no 3+. None of that is actually there in a resulting ion. So that's something that a lot of people have trouble with, is understanding that this Fe in the product side isn't Fe 3+, because it's not a free ion floating around. Instead, it is just simply solid iron, and solid iron isn't an ion. So we don't write it as such. We're just going to write it as Fe. So our equation is simply plus Fe, and then we'd actually write solid right there. And that's what we're left with. So we're able to predict the products by knowing which elements are swapped out for others, and then being able to do our crisscross rule like we did here in the bottom right-hand corner. The resulting atom that's kicked out is just in a state on its own. It's not a ion, so it's just going to be a regular element. So you don't have to put the charges on it. So the last thing we'd be asked to do is balance the equation. So let's pick an element and balance it first. So the first element we're going to do is oxygen, There's 3 oxygens on the left, there's 3 on the right, so oxygens are good. So now that leaves us with Al and Fe. Now I've said in the past that we want to leave the elements that have just a single to the very end because they're very easy to balance. But in this case, aluminum only has 1 and Fe only has 1, so it's actually pretty easy to balance. So let's just pick aluminum. There are 2 aluminums on the right-hand side, so let's put a 2 in front of the aluminum on the left, and that balances that. There are 2 irons on the left-hand side, this Fe2, so we're going to put a 2 in front of the Fe, and then that one's done as well. Double displacement reactions are very similar to single displacement reactions, except now we're going to get both of the ions switching. So in this case, ions of 2 compounds exchange places with each other. Reactants must be 2 ionic compounds. That's going to be very important, otherwise they won't split apart. And they both must be an aqueous solution. So the general formula is AX, the A being positive, the X being negative, plus BY, the B will be positive, the Y will be negative, is going to give us AY plus BX. And why is that? Well, the A and the B are going to switch spots. So now the A is with the Y, and the B is with the X. And we know which one it must go with, because again, the A is positive, the Y is negative. So we know they must go together. The B is positive, the X is negative, so they must go together. Now it doesn't matter if you write it as AY plus BX or BX plus AY. It's the same thing, and there's no right or wrong way of doing that part. So let's predict this one. Sodium hydroxide plus copper sulfate. So in this case, the sodium and the copper are going to be the things that switch places. The sodium is going to combine with sulfate to form Na2SO4, because that's how we make sodium sulfate, right? The sodium we know is +1. Sulfate is SO4 2 negative. They're going to switch spots, and you'll be left with Na2SO4, which is what we have here. The copper 2+ is going to combine with OH to form copper hydroxide. Now, how do we know it's copper 2+? Well, we need to figure it out from the reactant side. So when we have CuSO4 and we do the reverse crisscross, we would assume that it would actually be copper 1, but we got to check our anion. And SO4 is not -1, it's in fact -2. So we multiply that one by 2 and multiply that one by 2. So remember, it's the reverse crisscross with the check. So since we know that sulfate must have been -2, we know that copper must have been +2. So now we know it's copper 2+, as we see here. Now when it combines with OH negative, it's going to form CuHO2. So when it combines with OH negative, it's going to form copper hydroxide. And the reason for that is copper 2+, OH is 1 negative, you cross them, and you get copper OH2. And that's what we're going to get for our products. So let's make a little bit of space and write them out. So NaOH plus CuSO4 is going to equal to Na2SO4 plus CuOH2. So that's our equation. Now the next thing it's going to ask us is to balance the equation. So how do we balance the equation? Well, let's pick one of our polyatomics. We have 2 OHs on the right-hand side. We have 1 on the left-hand side. Remember, that was one of the tricks. If we balance one of the polyatomics, that might take care of 2 or 3 elements at the same time. So we're going to put a 2 there. Now, what does that give us? Well, that gives us 2 OHs on the left, 2 OHs on the right-hand side. That's good. How about our sulfates? We have SO4 on the left, we have SO4 on the right. So now we know that the oxygens are also taken care of, because there is 2 oxygens in NaOH plus 4 in copper sulfate. So that gives us 6 oxygens on the left, and it's going to give us 6 on the right-hand side as well. So let's take a look at sodium. There are 2 sodiums on the left because that 2 Na. There are 2 sodiums on the right because of that 2 Na. So the sodiums are good. We know the sulfurs are good because they were taken care of in the sulfate. So the only thing left is copper, and there's 1 copper on the left, 1 copper on the right. So we're balanced. Double displacement reaction. So I want you to pause the video and complete the equation for this reaction and balance it. Okay, so let's see what's going to happen. So we know this copper and the sodium are going to switch spots. But we need to figure out which ion of copper it is. So if you have CuSO4 and you do the reverse crisscross, you're going to get Cu plus 1, SO4 minus 1. And just like we talked about in the last slide, we know that sulfate is actually -2. So we multiply that by 2 and multiply that one by 2. So we know it actually has to be copper 2+ that's going to form. So what is it going to bond with? Well, it's going to bond with CO3 2-. So when you do the reverse crisscross, you're going to get CuCO3. Now it would have been Cu2, CO3 2, but you need to bring it to lowest terms. And we just did that ahead of time. And we're going to add that to the remaining atoms. What are the remaining atoms? Well, we're going to have sodium. That's going to be +1. And it's going to be bonding with SO4 2-. So when you do the reverse crisscross, you're going to be left with Na2SO4. Now we need to balance them. So let's take our polyatomics first. So on the right-hand side, there's SO4, and there's 1 SO4 on the left-hand side, so it's good. What about our carbonate? Well, we have 1 carbonate on the left, 1 carbonate on the right, so we're good. So we've taken care of, from doing just that, we've taken care of the S's, the O's, and C's, because we know they all must be the same. On the right-hand side, there are 2 sodiums. There are 2 sodiums on the left, so we know sodiums are taken care of. The only thing left is copper. There's 1 copper on the right, 1 copper on the left, and so we're good. So it's a pretty easy one to balance, because we didn't actually have to do anything. Recognition. So you need to be able to recognize which reaction is taking place. If you could do that, then you already have the tools and the skills needed to predict the products and complete the reaction, as well as balance it. So try these 2. I want you to pause the video and determine what kind of reaction is happening in each one of these. Don't complete the reaction, just write what kind of reaction is occurring. Okay, so let's take a look. If you have H2 plus O2, you have 2 things, and they're going to become 1 thing. And that's just our basic synthesis reaction. If you have 1 thing, you know it's going to break into other things. It can't bond with something else because there's nothing else to bond with. So you know this one must be a decomposition reaction. How about this one? You're going to have a metal, a positive, and you're going to have a ionic compound. So what we're going to do here is we're probably going to kick out the hydrogen, and this is going to be a single displacement reaction. HGO, that's just 1 compound. You know it's going to break into other ones, so that's going to be a decomposition reaction. KBr plus Cl2, that's very similar to this one right here. So we know this is going to be a single displacement reaction. We know this Br is actually going to be kicked out by the Cl2 So that's going to be a single displacement reaction. This one here, we have two compounds. So we know in this case, the Ag and the Na are going to switch spots. And this is going to be a double displacement reaction. And then the same thing with the last one. We know the magnesium and the hydrogen are going to switch spots. And we're going to have a double displacement reaction as well. Combustion reactions. Combustion means to add oxygen. Normally a compound composed only of C, H, and maybe O is reacted with oxygen in a process called burning. If the combustion is complete, the products will typically be CO2 and H2O. If the combustion is incomplete, the products will be CO or possibly just C and H2O. Combustion reactions. When a substance combines with oxygen, a combustion reaction can result. The combustion reaction may also be an example of an earlier type, such as this, which looks a lot like a synthesis reaction. So synthesis reactions can also be combustion reactions. If you have one thing reacting with oxygen, it can be a combustion reaction. The difference is a combustion reaction is also going to give off energy. So an example of a combustion reaction is burning a fuel like wood or gas. Combustion reactions. Combustion reactions involve light and heat energy being released, as I talked about on the previous slide. So although they can be things like synthesis reactions, they're going to have another product as well. That's going to be the energy being released. Natural gas, propane, gasoline, etc. are burned to produce heat energy. And most of the organic reactions produce water and carbon dioxide as a byproduct. So that's going to be your clue. As I said in this slide, back here, we're typically going to get carbon dioxide and water as a byproduct of a combustion reaction, unless of course you're getting other things burning with oxygen, like magnesium in this example. So the clue you got to keep in mind is that there's going to be energy given off, and there's going to be oxygen involved in the reaction. Combustion reactions. When hydrocarbon compounds, so that's CXHX, are burned in oxygen, these products are water and carbon dioxide. Hydrocarbons are compounds that only contain hydrogen and carbon. So for instance, C2H4, CH4, C2H6, etc. Anything that just has carbon and hydrogen are called hydrocarbons. Now typically these hydrocarbons are going to react with oxygen in a combustion reaction to produce our carbon dioxide and water. And then, like I said, we're also going to make a lot of energy as a result. Combustion reactions. Other elements, like I was talking about before, can also burn with oxygen. So a good example is magnesium plus oxygen. That's going to give us magnesium oxide plus energy. Again, the key is energy being created, oxygen being used. Second reaction, oxygen is being used, energy is a product. In this case, it's hydrogen gas plus oxygen is going to give us H2O plus energy. And this is the reaction behind fuel cell energy. And then another reaction, P4 plus O2 is going to give us P4O10 plus energy. And this is the reaction that happens with a typical match. If you strike a match, it lights on fire. This is the reaction that's happening. So you can see it's also a combustion reaction because we're reacting something with oxygen to produce a product and energy. Check your understanding. I want you to pause the video and name the type of reaction, finish the equation, and balance the following reactions. So for the first one, it's pretty basic. We're going to have H2 plus Cl2. This is going to be a synthesis reaction. You're going to take your H, which is positive, your Cl, which is negative. You're going to crisscross them, and you're going to be left with HCl. The second reaction is a little bit more complicated. You got to think of H2O as HOH for this reaction to make sense. And what happens is that the positive Ca and the positive H are going to be swapped. So the Ca is going to come in and it's going to kick the H out. So you're going to be left with H, and now it's never just H. Remember, it's always H2 because hydrogen is a diatomic. And what you're left with is actually CaOH. Now, if we take a look at the charges on Ca, it's 2 plus. OH, it's 1 minus. And when you cross them, you're going to get Ca1OH2. And again, the trick is to think of H2O as HOH. So when we kick out the H, it makes sense that we have the OH left over. Now we need to balance the first reaction. There are 2 hydrogens on the top left. So what we're going to do is we're going to put a 2 here and balance the hydrogens out. And that takes care of the chlorines as well. For the second reaction, let's pick an element and start with it. So let's try with calcium. So calcium, there's 1 calcium on the left, there's 1 calcium on the right, so it's good. Let's try hydrogen. There are 2 hydrogens on the left, and there are 2 plus 2, 4 hydrogens on the right-hand side. So what we're going to do is we're going to put a 2 in front of that. And now that's going to take care of the hydrogens. Now what's left is oxygen. There are 2 oxygens on the right-hand side, because that 2 goes there. There are 2 oxygens on the left-hand side, so we know that one's good as well. Check your understanding. So just like before, I want you to pause the video, name the type, finish the equation, and balance the following reactions. So for the first part here, it's a little bit tricky, I'd say. This is actually going to be a synthesis reaction. So a synthesis reaction, and if it's a synthesis reaction, we know they're going to combine to form a product. Now it's going to be a special kind of synthesis reaction. Since it's a synthesis reaction with oxygen, we know it's going to have some energy. And it's not just going to be a synthesis reaction, it's going to be a synthesis reaction and a combustion reaction. So what happens? Well, The CO and the O2 come together to make CO2. Now the last thing we need to do is balance them. So what's our clue that this is going to be CO2 and not, say, a single displacement reaction? Well, the fact that it's something bonding with oxygen, it's going to be a combustion reaction. And as we talked about before, our combustion reactions are often our synthesis reactions as well. And the only way to make this a synthesis reaction is to make one single product. And that one product has to be CO2, because those are the only elements that we have available. So now let's balance it. There are 2 oxygens on the right, 2 on the left, so it's good. 1 carbon on the left, 1 carbon on the right, so it's good. So that one is done. Now our last one, we have 1 reactant. So we know from that clue it's going to be a decomposition reaction. So what is it going to break into? We know it's going to break into our potassium. So this is a little tricky, but what goes with potassium? Well, it's only going to be really chlorine, because what we get left with is O2. Now, if you had written K2O, that would also be a fantastic guess for this particular question. So give yourself a pat on the back, because that would be a very good way, a very reasonable and logical way of answering this question. But the correct way that this compound decomposes is to break apart into KCl and O2. So now we need to balance it out. So how do we balance it out? Well, let's take a look at the Ks. The Ks are good. The Cls are good. There's 1 on the left, 1 on the right. The oxygens are not good. So now here's a trick. If you have an odd number on one side and even number on the other side, you got to make the odd number even. So we're going to put a 2 in front of it. Putting a 2 in front of it is going to take care of that odd number. So now we're going to have 6 oxygens on the left-hand side. To make 6 on the right, we're going to put a 3 there. But now we've messed up our other ones as well. Now we have 2 potassiums, 2 chlorines. We're going to put a 2 in front, and now we're good. So again, this is a little bit more of a tricky question. The only thing that you got to keep in mind is that in nature, certain atoms break apart into form certain compounds because it's easier for them to do. And in this case, it's easier for this compound to form into potassium chloride and oxygen than potassium oxide and chlorine gas. Something that will just come with experience. Check your understanding. Name the type, finish the equation, and balance the following reactions. But before you do, I need to give you a little bit more information. When this Fe goes off on its own, the ion is going to be Fe2+. And that's going to be very important when you're forming your products. So pause the video and answer these questions. So this is going to be a double displacement reaction. You have 2 compounds, and the Fe and the H are going to swap spots. When they do, you're going to be left with an Fe2+, because that's what I told you over here, right? That's going to be bonding with a Cl. Cl is +1, so we're going to be left with FeCl2. Plus, we're going to be left with a hydrogen, which is +1, and a sulfur, which is 2-. And when you cross them, you get H2S. Now we need to balance it. There are 2 Cls on the right-hand side. There's 1 Cl on the left-hand side, so we're going to put a 2 there, and that's going to take care of that one. Now there are 2 hydrogens on the left. There are 2 on the right, so that's good. Sulfurs are good, and so is the iron. Now how did I know to take care of the chlorines first? Again, out of experience, but also I saw that it had 2 on the right-hand side. There was only 1 on the left, so I decided to start with that one. Now for the second one, this one's a little bit more of an obvious one. In this case, the zinc is going to take out the hydrogen. They're both positives, and that's going to make this a single displacement reaction. And I didn't write the top one, this is a double displacement reaction. So the zinc is always +2, and it's going to bump out hydrogen, so it's going to be bonding with Cl, which is always -1. When you cross them, you're going to get ZnCl2 plus H. And remember, H is never by itself. H is always H2. And the last thing we need to do is balance it. So let's take a look at the Cls again. There are 2 Cls on the right, there's 1 on the left, so let's put a 2 in front of the HCl. That takes care of the hydrogens as well, because now there's 2 hydrogens on the left, 2 on the right, and there's 1 zinc on the right and 1 on the left. So we know that one's good too. So that concludes our lesson on types of chemical reactions.